But right, so the next one is we're talking about a bowling ball, and the person is sort of, I guess, kind of crouching downwards and just sort of heaving the ball up over some, it's sort of accelerating it over this 2 meter stretch at some constant acceleration from a height. Okay. Excuse me, Sam. They heaves a bowling ball with certain weight. Okay, so reminder that weight is not quite the same thing as mass, so you'll have to convert. You'll have to convert pounds to kilograms, probably. Probably. I don't know. Look at the problem to be sure. But giving it a constant upward acceleration from rest for a height of. Okay, gotcha. So I guess what they're saying is it's being accelerated over some delta y is equal to 0.7 meters. But then the actual height itself is 2 meters at the point of release. So those are just two slightly different numbers, right? It's sort of like saying he's not picking it up from the. I guess it's saying he's not picking it up quite from the ground, but like some midway position, and then throwing it upwards. So just make sure to get that clear. But it's asking what is the speed of the bowling ball when he releases it. Okay, so let's continue to get that practice with the kinematic equations, right? Of the ones that we do know, okay, so we are given the acceleration. We know the period over which it moves. And we also sort of know that the velocity initial is equal to 0 because it's kind of implied that it's from rest. So with this in mind, one equation in particular should jump out for us to find the final velocity, or the velocity upon release. Right? Which equation is that?
Oh, after just looking at the equation, I mean the question, there'll be two unknowns, right? It'll be the v final and time.
Uh, yeah. What is it asking us? There's asking the speed of the bowling ball. How high does it go? How much time does he have to get out of the way? Just for sorry, don't even worry too much about that many unknowns. Just to get the velocity at the time of release, we should just need a single equation for that, right? Because we know v naught, we know the change in y,
It'll
and we know
be
the
v
acceleration.
it'll be vf squared equals
Exactly. Right. So I'm going to call this. I'm going to say t naught is at rest. I'm going to say t1 is at release. So this is going to say v1 squared is equal to v naught squared plus 2a change in y. Okay, so that basically lets us find v1. Very good. And then it's asking how high above the ground does it go? Well, all right. So that's basically saying, all right, it's going to jump up to some maximum height, and then, and remember, let's just call this time t2, right? So t2 is at peak. t2. And like before, you know that at the peak, the velocity is going to be 0. So v2 is equal to 0. So I think, again, one of the equations is going to be a lot more promising than the others. If we want to know the total height differential from the point of release all the way up to the peak, I think this exact same kinematic equation is going to be most useful for us. Because that's basically saying v2 squared, which is just 0, is equal to v1 squared plus 2a change in, I'll call this y, 2 comma 1 to indicate that it's the change in y from time 2 to time 1. But yeah.
Did you swap the v initial with the v final, or will the v final be 0 in this problem?
So what do you mean by swap, right? I'm sort of saying this equation describes an interval of its trajectory. So from the interval where it gets released to the point where it reaches its very peak, the initial is going to be v1, which is at the point of release, and the final is going to be v2, the point of peak.
Oh, okay.
So it's sort of describing a different interval. It's not so much being swapped. Does that make sense?
Yeah.
Yeah, okay, very good.
Could I ask a quick question about the
Of course.
equation?
What's up?
So, first one for delta y, would you use the height that they give you when he releases it, or
Exactly.
the other height? 'Cause he gave you 2.
Yeah, so that's a great question, and that's sort of what I was that's what I was alluding to when we were talking about two different things earlier. Just by the wording of the question, it says that the constant acceleration is over, is over a certain period, over a certain track length almost. So yeah, you would take this one and plug it in over here. The height of the 2 meters or whatever it gives you is just for calibration when it later asks how high above the ground does it go, period. Does that make sense?
Yeah.
Just by
thank
reading the
you.
question, it tells us that this is the acceleration track length as opposed to this one. Great question. Thanks for clarifying. Thanks for asking. But yeah, and if the last part is asking how much time does he have to get out of the way before it returns to the top of his head. So I guess I don't know if it's asking the time after release or the time from the peak, but I'm sure you can find it really either way, right? So if this is basically saying, okay, so we know let's say time 3 is at head height.
Would that be the maximum height initially?
No, T3 is going to be at head height, which is sort of saying when it goes, all the way up and then comes all the way back down. That's going to be my idea of T3.
So the distance will be negative.
Exactly, distance will be negative. So you just take whatever the initial release height was, which was 2 meters or something like that, and then that's sort of the quote unquote initial height, and the final height is just whatever his head is, like I don't know, 1.8 or something. So then that's basically delta y is head minus initial release height is equal to whatever v1 t3 minus t1 plus 1/2 minus g t3 minus t1 squared, right? And this time around I sort of just gave away the kinematic equation, but I hope it's relatively clear because you knew the initial velocity and you're being asked to find the t3 minus t1, right? Yeah, you're not being asked to find T3 and T1 independently, but you're asked to find the difference T3 minus T1.
Oh, when you're referring to T3 and T1, as in we'll input T3 into where T3 belongs and T1 where T1 belongs in that kinematic equation, or
so for a problem like this where we don't get too much information about when T1 actually happens and when, like, how do you put it? We're not given it too much information about when they happen absolutely. And the question only asks us about the relative difference between them anyways. So if you really just wanted to treat this in your head as just another variable, delta t, and think about solving for delta t squared, sorry, if you want to think about this just as delta t and solving for delta t instead of t3 minus t1, you can do that as well. Do you see what I'm saying? Like, the problem doesn't care about the value of t3 itself or the value of t1 itself. It only cares about the difference between them.
Okay.
Yeah. Okay, very good.